Okay, so a third way to do this is using an algebraic rearrangement or arguments as well. So if we look at the this graph here, this is a rational expression where the numerator is 1 greater than the denominator, and we know that these ones tend towards slant asymptotes. So what we've done in the past, and this is was our argument in the past, is that if we do long division, we end up with a quotient. Our quotient of when we actually do the divide is going to be 2x plus 3. And we have a remainder of 5. And if we write it in its division form, it's going to be 2x plus 3 plus the remainder over divisor. So as x goes to infinity, we know that this term tends towards 0, okay, because we're dividing by infinity. And the graph behaves like this asymptote here, so 2x plus 3. So we say that the graph, as x gets large, it starts to behave like this linear function 2x plus 3. And this is how we can do some algebraic rearrangements to be able to do that. Okay, so we've done this in the past when we looked at rational functions, okay, and with slant asymptotes. The other one is when we look at relative powers of x, we know that some functions are more powerful than others, so they grow faster than others. So we have linear functions here. Our linear functions are kind of the middle standard. F of x equals x. So, and as we increase the powers of polynomials, we know that those grow faster than x's. Okay, so polynomials, so this one here is a polynomial. X to the power n represents some power of polynomial, and these are more powerful than linear functions. And the greater the power, the more powerful the function. We could go in the opposite direction and do roots. Okay, so if we have a squared here, we have an opposite as root. And these are less powerful than linear functions. The next level is when we go to exponents. Exponents are functions that grow more powerfully than any polynomial. And the reason why it does is because we have the power of infinity. Because it doesn't matter what the power is here, this power will always get bigger than whatever power we set here. This could be x to the power 1 billion, but this will get much bigger than a billion. Okay, so this exponential function then is the next most powerful. Okay, so any exponential will always outgrow a polynomial. And the converse is true. The log function is going to be the weakest because it's going to be weaker than any root function. Then I've added one more here, the factorial. The factorial happens to grow the fastest, even eventually outgrowing the exponential, because the factorial, the base essentially is going to get bigger, whereas this base stays the same. This has many, many multiplying terms, just like the exponential, but this base is also growing at the same time. So how can we use this property for limits at infinity? And again, these are only for endpoint behavior and limits at infinity. Okay, this does not work when we're doing local behavior. So when we look at this ratio here of x divided by log x, we can make this argument. We have on top a stronger function divided by a weaker function. So we have this strong over weak. Well, if it's strong over weak, it's going to tend towards infinity. Okay, so we can make this limit, we can evaluate this limit using this relative strength of function. And again, the same thing can be done if it's the opposite. Now we have weak over strong. Well, this infinity is way stronger than this infinity on top. So we end up with this situation where this one's going to tend towards 0. Okay. Here we have sine x, which just bounces up and down between 1 and -1, and log x. Well, here we're going to end up with, this is going to be plus minus 1. That's the maximum that's going to achieve. But the denominator, although it grows slowly to infinity, it still goes to infinity. So anything divided by infinity, whether it's positive or negative, it's going to tend towards 0. Okay, it's going to actually bounce back and forth. Okay, it's going to kind of go bounce back and forth, but it's going to eventually tend towards zero. Although it goes positive, negative, it tends towards zero. So this one here, we have really powerful polynomials on top. Okay, power 23. In fact, we don't really even worry about those ones. We just look at that power 23. However, although that's a really powerful polynomial on top, we've got a more powerful function on the bottom. So again, this one we can make an argument. Although this is strong, it's weaker than the exponential. So again, we have a stronger function on bottom and a weaker function on top. This is going to tend towards zero. Okay, and again, this is going to be the same thing, except now the log function is, although this is a really weak square root function, the log function is always going to be weaker. Okay, so although we have weak on bottom and weak on top, we have really weak on top and something that's a little bit stronger on the bottom. Well, those situations, when we go to infinity, again, I want to stress this is only good for endpoint behavior to infinity. But when we have this situation of weak over strong, we end up with a limit equaling zero. Okay. Now with limits, again, the best way to do limits is to graph them. So we should look at these graphs just to confirm these what we got here. So we had infinity for the first one. The rest of them tended towards zero.